Hi, folks. Welcome back. We're on section 2.3 today. Let's get started. So, given a system of equations, ax equals b, we might ask ourselves these questions about the system. For what values of b can we solve this? Does a solution exist? Can we solve it? And then, for what values of b is there a unique solution? When can we solve this in more than one way versus just one way? Can we solve it in multiple ways or just one way? And so we're going to look at these questions. We're going to look at this question in today's video, and then we're going to look at this question next time. So I have to cover some definitions, but we'll have the tools to answer this question by the end of this video. Let's get started. So here's our definition. If we have a set of vectors, the span of that set of vectors is all of the possible vectors that we can build as linear combinations of those vectors. That is, the span is every vector that is can be made out of a linear combination. And so if every vector is in that span, then we say that the set of vectors spans Rn, spans the whole set Rn, in other words, not just part of it. Or sometimes we say it's a spanning set for Rn. So let me sort of walk through what we're talking about here. So let's say we're in R3. And we have these two vectors. Let's say this is vector v1, and there's some other vector v2. And I can build linear combinations of these vectors. For example, I can take 2 times v2. I can take 2 times v2 plus v1. I could take 3 times v1 plus 4 times v2. And I could take negative v1 and negative v1 minus v2. But no matter what combination I build, I'm limited to only vectors that are in this plane that contains v1 and v2. I can only move in the v1 and v2 directions. And so if I wanted to look at a vector that was, like, say, perpendicular to that plane, this vector is not a linear combination of v1. And so the span only contains the vectors that are linear combinations. In this crude example here, the span is this plane here. This plane is the span of v1 and v2. I can build every vector in that plane using combinations of v1 and v2, but I can't move outside that plane just using these two vectors. So that's the idea of a span. It's the vectors that we can build from the set that we're starting with. So let's look at this example. We have these two vectors, and we want to know if we can build the vector 5, 3 out of these two vectors. So by the definition is that the span V contains all linear combinations. Of the vectors in V. Is 5, 3 one of those linear combinations? And the answer is, well, Yes, but we're going to show that in a moment. That is, in order to be a linear combination, there have to be weights that we assign to the vectors. That makes this linear combination work. And this is equivalent to solving the system whose augmented matrix looks like this. Now I'm only going to do one row reduction step here. And the one row reduction step I'm going to do just to put this in echelon form is to get rid of this 3 and change it to a 0. Since 3 and 4 don't play nice with each other, we're going to have to find their lowest common multiple, which is 12. And so I'm going to take 4 times row 2 minus 3 times row 1. All right, so 12 minus 12 is going to give me 0. 4 minus 6 is going to give me negative 2. And 12 minus 15 is going to give me negative 3. Now, I've only done this one row reduction step. But what I find now is that x is basic and y is basic. And the last column is free. And this is important because what this means is that we do have a solution that we can solve the equation negative 2y equals negative 3. Then once we have that solution, we can solve x minus 2y, 4x plus 2y is equal to 5. What makes a solution not exist is having a leading entry in the augmented column. That is, we don't have a row like 0, 0, and then something over here that's not 0. And so there is a solution. I haven't taken the time to find it. I don't know what the solution is yet, but I know that there is a solution, and that's all I need to know to answer this question. Yes, this vector is in the span. I can reach this vector with a linear combination of the vectors, and if I took the time to finish solving this, I would know what that linear combination is, but I already know that, yes, it's possible. All right, so let's move on. So in this example, we want to know why every vector is in the span of RV, and not just 5, 3. So let's go back and look at what we did in the previous diagram. And so I'm going to turn myself off again. We're going to go back. And when we did this row reduction here, it didn't really matter what these two numbers were. That this number became 4 times this number minus this number. But no matter what these two numbers are, no matter what these are, my leading entries will still be here. The augmented column will never have a leading entry. And as a result, this answer turns out to be yes. In this problem, it turns out to be yes no matter what vector goes here, because these two entries line up in a way that blocks the third column from ever possibly having a leading entry. And so we go back here and let's sort of explain what happened here. Both rows have leading entries on the left side of the matrix. And so there can never be a leading entry in the augmented column even if we change 5, 3 to some other vector. And so every vector in this case is in the span of V. Now, geometrically, that shouldn't be too surprising because we're only in R2. So we only have an x coordinate and y coordinate in our system. And if I look at these two vectors, 4, 3, and 2, 1, those point in slightly different directions. And if I start taking all of the linear combinations I can make, traveling along in the 2, 1 direction for a while, and then switching, and then traveling in the 4, 3 direction for a while, and I can go positive or negative in the 2, 1 direction, and then I can switch and then go into the 4, 3 direction for a while. Then what happens is I get these linear combinations that all lie in this plane, but this plane is the plane. There's only one plane here. And so every vector in xy is eventually going to be part of this plane. All right. So going way back here, in 3 dimensions, when I only had 2 vectors, they generated a plane, and a plane isn't all of 3 dimensions. But in 2 dimensions, the plane is all of the 2 dimensions. And so these 2 vectors, every vector is in a span of V. All right, let's move on. Let's take this vector. Show that 5, 2 is not in the span of these 2 vectors. Okay? So we're going to try solving this system here. -2, 8, 5, 1, -4, 2. And when we put this in echelon form, so I want to take 2 times row 2, add that to row 1. 2 plus -2 is 0. -8 plus 8 is also 0. And 4 plus 5 is 9. And now we have a leading entry in the augmented column. This tells me that there are no solutions. And so, 5, 2 is not a linear combination. Of -2, 1 and 8, -4. And so the answer is that this vector is not in a span. Geometrically, what's going on here is if I look at these 2 vectors, and I'll try to draw this carefully here, -2, +1, is this vector here, and positive 8, negative 4 turns out to be an exact multiple of this vector. 6, 7, 8, 1, 2, 3, 4 is just the same as negative 4 times this vector, which means it points in the opposite direction. And so this is negative 2, 1. This is 8, negative 4. And if I take these linear combinations, any multiple of 2, 1 is going to be on this line, and any multiple of 8, negative 4 is going to be on this line. And so even though I have two vectors, because they point along the same line, I don't generate a plane from these two vectors. I only generate other vectors that are on this line. And so we can't just count the vectors and say, since it's two vectors, that's going to be one direction, another vector that direction, that forms a plane. They might be in the same direction. And so we do have to sometimes check this here. But the important thing is, does the last column, the augmented column, does that have a leading entry when we're all done? And that will help us answer the question. All right, let's move on. So let's write an equation for the span of these two vectors, and then describe the span geometrically. So the first part, writing the equation for the span in linear algebra, is really surprisingly easy. That it says that my vector xyz is a linear combination of these two vectors. So I need two weights. And this time I don't want to use x, y, and z because I've already used them here. So I need a weight for each vector, but can't reuse the letters y and z, x, y, and z. So I might use S and T, or I might use A and B. I don't care which letters you use, but if I let S be the weight, 160, and T be the weight of 961, negative 1, these are all the linear combinations. And by definition, that is the span. The span is the set of all linear combinations. So writing the equation for a span is really a straightforward process. You just have to remember what that process is. It's just form the set of linear combinations and assign that to a vector. So if we want to describe this geometrically, so we're in 3 dimensions here. The first vector is 1 unit in the x direction and 6 units in the y direction. 1, 2, 3, 4, 5, 6, and no units in the z direction. So that's our vector u. And then the other vector, v, is 9 units in the x direction. 6, I have to extend this, 7, 8, 9. Still 6 units in the y direction. And then down 1 unit from that. So that's going to be our vector v. And because I can multiply u by any constant, I can get any multiple along this line here. And then I can add to any point on this line a multiple of v, a multiple of 961, and v goes in this direction. So I can go from any point, any amount I want to in these directions. And so that generates a plane that travels in the u direction and the v direction but again, does not travel in a direction that's perpendicular to that plane. And so the span geometrically, this is a plane that, in our sort of sense, it looks like it sort of goes up and down with maybe a slight tilt on it because one of the vectors, the u vector, is on the xy plane, and so the surface goes through that. So this geometric description might be that this is a plane inside R3. Okay. All right. So let's find an equation for the plane. Okay. So because we now know that a plane is the span of two vectors that have different directions, I just need to create two vectors out of these 3 points. The origin, the point 1, 0, 2, and the point -1, 1, -2. So that's going to be this point down here. Well, those two vectors could be just this vector and this vector. So my vectors are 1, 0, 2, and -1, 1, -2. And because planes are spans and the equation for a span is easy, we can write the equation for the plane in parametric form by using 1, 0, 2 and a parameter, and -1, 1, -2 and a parameter. So s times 1, 0, 2 plus t times -1, 1, 2. And that's it. Now, as a side note, some of you have taken multivariable calculus already. Some of you are taking it right now. Some of you will take it in the future. And you learned a different process for finding the equation for a plane that involved using a cross product to find a normal vector, multivariable. Used a cross product, used a normal vector to the plane, and that process may have seemed much more difficult than what we just did here. The advantage of the processes found in the multivariable class is that you get a non-parameterized equation for the plane. So that process is correct and gives a non-parametric result. So once you get out of both classes, you can do this as a parametric solution or as a non-parametric solution, depending on what you need. But the parametric solution is definitely the easier one to do, and so that's the one we're using for this class. So if you haven't taken multivariable, or if you're not planning to take multivariable, the side note doesn't apply to you, but I just sort of want to clarify, we cover two different ways of finding the equation for a plane. And that's not meant to confuse you. It's meant that there's two different forms for that equation, and we eventually get you through both of them. All right. So number 5, I think, is pretty similar to number 4. Find an equation for the plane that contains these 3 points. The one tiny thing that makes example 5 a little bit harder than example 4 is that the origin is not one of our 3 points this time. So if we visually look at what's going on here, I have these 3 points, 3, 1, 2. So that's 3, 1, and then we go up 2 units. That's one of the points. And then 4, 3, and then we go up 8 units. That's going to be much higher. That's going to be one of the points up here. And then 6, 2, and then 7. And that's going to be one of those points over here. And so we're looking at sort of this plane here. What we need are 2 vectors. And in the last example, this was easy because we could make the vector start at the origin. We don't have the origin this time. So we have to pick one of these to be the starting point. So if we let this one be the starting point, and it doesn't matter which one you let be the starting point. So we'll start at 3, 2. Then my vectors are these 2 vectors here. And the coordinates of the vectors are the displacement between the start and the end point. So the first vector, in the x direction, we go from 3 to 4. That's 1 unit in the x direction. In the second vector, that's 1 to 3. That's 2 units in the y direction. In the third vector, third coordinate, that's 2 to 8. That's 6 units. And I'm not adding them yet. The second vector goes from 3 to 6, so that's 3 units in the x direction. 1 to 2, that's 1 unit in the y direction. 2 to 7, that's 5 units in the z direction. And so if we look at the span of those 2 vectors, this is what we get. We get s times 1, 2, 6 plus t times 3, 1, 5. But this is not quite right this time. We're not done yet. Because when s and t are 0, this gives me the origin. This plane doesn't start at the origin, it starts at 3, 1, 2. So this is a plane that passes through the origin at s equals 0 and t equals 0. We need a plane that passes through 3, 1, 2, and so we have to shift everything by 3, 1, 2 to guarantee that it goes through our starting point. So shift the starting point from the origin. And now when s and t are 0, then we get 0 times this vector plus 0 times this vector plus 3, 1, 2, and that means that at the starting point at s equals 0 and t equals 0, we're here and not down at the origin. So a couple of extra things we have to do if the origin is not one of our starting points. We have to take these 2 points and find 2 vectors in order to write the span. And then we also need to include the starting point in our solution as well. Okay? All right, let's move on. So when does a set of vectors span Rn? So these 2 statements mean the same thing. They're just 2 different ways of saying the same idea. Using our new language, spans, we can say that the set of vectors spans the entire set Rn. That's another way of saying that every vector is a linear combination of the vectors in Rn. So that it means that we can make a linear combination no matter what value is on the right-hand side of the linear combination. But the second statement, if every vector is a linear combination, that tells me something about the echelon form. So if I have a system of equations here, and I don't know how many rows or columns are in this system, I'm just sort of doing an example now, that if this is always going to be the solution, no matter what goes here, that tells me that I have to have a leading entry in the first row over here, because if I didn't, let me show you. If this was 0, 0, 0, 0, then I could put a 9 here and then there wouldn't be a solution. And we're told that there's always a solution. That the second statement, let me back up here. Second statement says every vector is a linear combination. And so we always have a solution. And that means the top row of this echelon form can't be all zeros. And therefore, we have to have a leading entry in the top row. But then this argument carries on to every row. This row can't be all zeros, because then I could put like a 7 here and then this wouldn't be a solution. And so in the echelon form, this row needs a leading entry. And then this row can't be all zeros, because then I could put a 5 here and we wouldn't have an answer. So I have to have a leading entry over here. And finally, the bottom row, same thing. That means that every row must have a leading entry before the column, before the augmented column. And we're going to summarize this in a theorem on the next page, but this gives us a test for being a spanning set or not. So if we have a set of vectors, then the span is all of Rn if the matrix just containing V1 through Vm. This is the coefficient matrix, not the augmented matrix. Because it stops at Vm, which is the vectors on the left side of the equation. So if the matrix has a leading entry, if that matrix has a leading entry in every row, then no matter what we augment it with, we can't have a leading entry in the augmented column. And that's what guarantees us to have a spanning set. So what we now know is the significance of having a leading entry in every row. Later on in the next video, we're going to talk about what the significance is if there's a leading entry in every column, and that turns out to give us some information as well. But leading entry in every row is what guarantees that the set of vectors spans all of Rn. All right, so let's try an example, and then we're going to wrap up. So this set of vectors, and the instructions are missing here, so let me fix that up for you. The set of vectors spans R3 for what values of k? Sorry that that's missing from the slide. I will have to fix that up. So we have a set of vectors, and we want to know when it spans R3. So based on what we saw before, we're saying that if we start with 1, 2, 1 in the first column, 2, 6, 5 in the second column, -1, 3, and k in the third column, and then we row reduce, and remember that this symbol here means that it row reduces to whatever matrix it has to have 3 leading entries. Which means the bottom row cannot be all zeros. So let's give this a try. So we're going to start row reducing this here. 1, 2, 1. I'm writing this vertically. 2, 6, 5, -1, 3, k. So I want to get rid of this 2. So we'll take row 2 minus 2 times row 1. 2 minus 2 is 0. 6 minus 4 is 2. 3 plus 2 is 5. And now I want to get rid of the 1. So that will be row 3 minus row 1. That will be 1, 2, -1, 0, 2, 5. And now the bottom row is 1 minus 1 is 0. 5 minus 2 is 3. K minus a -1 is k plus 1. All right. Now we want to get rid of the 3. And so we need to take row how are we going to do this? I don't want to use row 1 because that 1 will come back down here and contaminate the 0 we've got. So I have to use row 2, and that means I have to use the lowest common multiple trick. So I'm going to take 2 times row 3 minus 3 times row 2. Let's make that happen. 1, 2, -1, 0, 2, 5. 0 minus 0 is 0. 6 minus 6 is 0. And for the last entry, that's going to be 2 times k plus 1 minus 3 times 5. That's 2k plus 2 minus 15, or 2k minus 13. And we have to have 3 leading entries, and that means that 2k minus 13 cannot be 0. Because if 2k minus 13 was 0, then we would not have a leading entry there. And so 2k cannot equal to 13. And so k cannot equal to 13 halves. And so for what values of k? All real numbers except for 13 halves. And the set of vectors spans for all of those vectors. All right. We're done for today. Thanks for watching. See you next time.